So what we did so far was I showed you how to get the pendulum to go from 0 to 90 degrees in one shot, right? But that's not what you want to do, because that just makes the system very jerky, right? Imagine going from 0 to 90 degrees in 0.5 seconds. That's not what you want. What you want to do perhaps is to get the system to go from, let's say, 0 to pi divided by 2, which is here, in say 3 seconds. So in this case, you want to have some kind of trajectory which you want the pendulum joint to follow, right? And we've seen how to generate trajectories before. For example, one trajectory which minimizes the transients is to use a polynomial, right? Use a third order polynomial, a0 plus a1t plus a2t square plus a3t cube. And how do we get this? Well, we say that the initial position is 0, the final position is, let's say, a capital T is pi divided by 2. Then the initial velocity is 0, and the final velocity is also 0. So based on these conditions, we can get these constants a0 through a3, and that gives us q as a function of t. And we want the system to follow this q. So this q is actually our reference motion. We call it q ref. Okay. So the next part is, our goal is the joint should follow reference trajectory. Okay, so here we have again the same dynamics. Dynamics are not going to change. The controller, however, is going to be slightly different, not too different from what we had before. What we do is we write the torque as m hat like usual, and then we specify qd double dot plus, minus, my bad, this should be ref, kp q minus q ref minus kd q minus q ref, and that should be derivative, plus g hat q plus c hat q dot times q dot. Okay, so what change has happened here is, the only change is right here. We actually specified the accelerations and so on. Okay, so let's analyze the system. Okay, for the simple case when m equals m hat, g hat equals g, and c hat equals c. So let's put this inside this equation, the first equation. So let's put 2 in 1, and the way it changes is that you need to substitute the value of torque. So we have m q double dot plus c q dot times q dot plus g q equals m hat q double dot ref minus kp q minus q ref minus kd q dot minus q dot ref plus g hat. Well, g hat m hat is m, so I'm just going to eliminate the hat. Okay, now what we see is, from the left hand side we can eliminate or remove c, we can cross out g, and what we're left with is something like this: m q double dot minus q double dot ref. Right, I'm pulling this to the left side, plus, so the m comes out, it's basically something we can factor out, and we're left with kd, I'm going to write this first, q dot minus q dot ref plus k p q minus q ref equals 0. Now we take this expression and move it to the next page. Okay, now what we can do is we can write q minus q ref is basically the error, right? We want q ref to be q because we want q to follow q ref. And so if you write that as e, then we can see that this is simply m times e double dot plus kd times e plus kd times e dot, sorry, plus kp times e equals 0. And since m is not equal to 0, the mass matrix is not 0, we can see that e double dot plus kd e dot plus kpe equals 0. So this is similar to our expression we wrote down earlier. We wrote down q double dot plus kd q dot plus kpq. Right? And for this system, we have actually a simple controller. It's basically, we only need to ensure that kp is 2 square root, or kd is equal to 2 square root kp. This is the critically damped system. So what we've done is we've taken a complex system, used control partitioning to simplify it to this simple form. And once we reduce it to the simple spring mass damper type form, which looks like this, we can then choose a critical controller. And now this is doing reference tracking. So here is the block diagram for such a system. Okay, so let's start off with the system on the right corner. Okay, what's fed into this is the torque. Okay, the torque, the output of this is going to be q dot and q, and that will go into k, sorry, this should be g. So g gets multiplied with q, so that's there. And then q and q dot both go into c, because c is a function of, I didn't write it down there. C is a function of q and q dot. So next I'll put c. So both of these will be inputs. Okay, so if you want, you can put a hat. And what happens is these two blocks add on to okay, let me write this down. This is much easier if I write down the formula here. Kp q ref double dot minus kpq minus q ref minus kd q dot minus q dot ref plus g hat, so it's g hat times q plus c hat q dot q dot. Okay, I'm just trying to write this down in the block diagram. So I'm working on these terms. So c that comes here and adds up, right? So that takes care of these two pieces. Here I would have a mass matrix, this one, which multiplies with this whole term. So I somehow need to get this term in there. So I'm going to do is draw another circle. And I need, let's see, I need some reference. So let me just pull that and make a new, move this down first. Okay, so I need a reference. So let me just create a reference signal. Q ref, q dot ref, actually, and yeah, q dot and q ref. And let's see what's happening is I need to do q minus q ref. So I need to take q, which is here, and then I need to take q ref, and then I need to subtract one from the other. So I need to do negative q ref, and positive for q. What comes out of this is q minus, sorry, it should be q with a positive sign, q ref with a negative sign. That will go into the block which multiplies with kp, and then that would go in here. Similarly for q dot ref, a circle, q dot comes to the circle, plus minus, this would go multiply with kd, make it cleaner this way. Okay, kp, kd, and then the last piece, so this is going to be subtracted, so negative sign, and then subtraction, negative sign, and then finally this part is missing, which is q double dot ref. Okay, that is the the block diagram for control partitioning with trajectory tracking. Would be trajectory tracking of a single link pendulum. Okay, so the pendulum is in this position to start with. Gravity is downwards. The goal is to get this pendulum to go upright, okay, in this position, and then go back to the horizontal position. So we want to get the pendulum to go from, so let's say that the angle of the pendulum is given by theta. So at time t equals 0, we want the pendulum to be at 0, which it is. Then at time t equals 1.5, and I just chose 1.5 to be some arbitrary value. We want the pendulum angle to be 90 degrees. And so we also want to ensure that at time t equals 0, the position is 0, and then the velocity at 1.5 is 0, right? So based on these 4 conditions, we can write a formula for a polynomial which basically ensures that all the 4 conditions are met, and that would be something like this. It would be a third order polynomial, 1 0 plus a 1 let's see, 1 t plus a1 3 t square plus a1 4 t cube. Okay, and we can find the a's based on the 4 conditions. Okay, so we've done that, so I'll not do that again. And then what we want to do is we want a pendulum to come back to the horizontal position, which means that it needs to start at 1.5 with a position of pi divided by 2, which is 90 degrees. And then at 3 seconds, which is again randomly chosen, it should be back to the horizontal position. And then it does so with a start speed and end speed of 0. So again, these are 4 conditions. You would have a polynomial of this type, a20 plus a21 t plus a22. This should be 2 and this should be 3, just to be consistent. T square plus a23 t cube. So again, you can find a's based on the 4 conditions. Okay, so you do that for both these polynomials, and then you can use this control partitioning for the torque. So there's a single torque here with a kn kd equals 2 square root of kp. And then you should see that the pendulum actually follows the trajectory which you created, which is basically this theta for the first half from 0 to 1.5 and then 1.5 to 2. So that will be the first example. I'll show that to you in a bit, but let me show you the second example, which is, so I'll just formulate the problem and then I'll show both these examples together. The second one would be a double link pendulum. Okay, and so the pendulum is, the equations of the pendulum are derived with the horizontal in mind. So which means that this angle is theta 1 with the horizontal and theta 2 is going to be the angle with respect to the first link, right? So that's the two link pendulum. The problem which we're trying to solve is we're trying to generate a sort of a kicking motion for the two link pendulum, which means that we want the pendulum to start in this position, then move this, sorry, my bad. We want the pendulum to start in this position. Okay. Next, we want the as you can see, the calf the calf and the thighs, the thigh and the calf, because we're simulating a kicking motion. We want the calf to go backwards slightly, and then we want both these links to move. So this moves backwards, this keeps moving forward, then we want to end in this position. So this is going forward, right? And we want to do that, let's say, in 3 seconds. So first, what we'll do is, so let's call this link 1, link 2. For link 1, the angles, as I said, as theta 1. So what I want to happen is, I want theta 1 to go from, let's see, so I just arbitrarily chose it to be, so since this is, the angle is measured with respect to the horizontal, this angle is minus 90 degrees. So I want to start really here from, let's see, minus 90, which is minus pi divided by 2, minus 0.5, which is just saying that this angle is 0.5 with respect to the vertical. Then I want it to go all the way to minus pi divided by 2 plus 0.5, which means it goes with an angle of 0.5 and plus 0.5. So this is minus 0.5 plus 0.5 with respect to the vertical, right? That's what's happening. And I want this to happen in 3 seconds. So the time goes from 0 all the way to 3 seconds. So this is for link 1. Now we also want to ensure that the velocity, so theta 1 dot, is 0 at the start and 0 at the end. And so we can write an equation which is a third order polynomial and solve for a's. Okay, so that's for link 1. For link 2, since we want to reverse the motion in the first half and the second half, so we want to look at two polynomials. The first polynomial will basically start, so we'll start theta 2 with an angle of, see, 0, which means that it's perfectly aligned with the link 1. Then it goes backwards, so it goes to minus pi by 2, which is, as I said, it's basically minus 90 plus 0.1. So this is just ensuring that it goes slightly negative. Then the difference between these two is minus 0.57, which means that this angle is going to be minus 0.57. Right, and then it goes back to 0, because you can see here it ends up with such that link 2 is aligned with link 1, and then the time, let's say, goes from 0 to 1.5 to 3. Okay, so you can see that here we have only one clock 0 to 3, but here we have two windows, 0 to 1.5 and 1.5 to 3. And then the same thing, we want to ensure that it starts with 0 speed, ends with 0 speed for each of these things. So then for theta 2, we will have two such polynomials, a12t plus a13t square plus a1 should be 1 plus a12 t square plus a13 t cube. Okay, that's for the first part. And then the second part, so that will be t from 0 to 1.5. And then we have a20 plus a21t plus a22t square plus a23 t cube for the time from 1.5 to 3. Okay, so it's a little bit more complicated than a single link because, first of all, we have two links, and second is we've broken down the motion to two parts for link 2. Okay, so I'm going to show you how this is done in MATLAB. Okay, so there is, I'm opening quite a few files which I think are relevant to this particular example. One link pendulum, one link traj, and as I said, this is how the single link pendulum looks. Okay. So what I did was I basically use one link trash to generate the trajectory. So you can see that I've defined symbolic variables for the two polynomials. And then I actually do this with MATLAB. I don't even write it down on paper. You can do this following this example. Define the start for the time, start for the angle, same for segment 2. Right, and then you can use what is known as, well, you can use differentiation to get the derivative, but then you can use substitutions to find the values. Now, what I realized is that this actually is a little bit more, I enforce more conditions than what I wrote on paper. On paper, I just wrote down it satisfies the velocity at the start and end as 0. But here actually it turns out that I actually also enforce the acceleration to be 0 at the start and end. That means that I need more than, this doesn't seem to be right to me. Okay, though I define theta1 d dot, I don't seem to have used it. Okay, so my bad. So I actually have, let's see. Okay, I see what I did. I think I combined both of them into a single equation. Okay, so basically this gives you the A and the B matrix. And then once you get those, if you run this, it actually might throw an error because it's supposed to be called, oh no, it just derives the equations. There it is. So it basically gives me the A matrix, sorry, the coefficients for those two trajectories, which I can then copy paste in the code one link main. This is the main file, which basically will do the necessary simulations for me. So this is the position velocity, same position velocity. I wrote the acceleration just to show you the acceleration discontinuous, but that is not really used to get the coefficients. Okay. And so that is basically the copy paste has taken place here. This is what has been copy pasted from the command window. Okay, so let's run this first. Okay, so this is showing the black dashed line is showing the reference and the red line is showing the actual. This is for the velocity. This is for the position. So you can see that the velocity is not tracking the reference. The blue line should have tracked the black dashed line, same for the red one. And that is because I actually, two things. One is I introduced a disturbance. So even though the mass matrix is 1, I actually said that the estimated mass is 1.5. And in order to ensure that I track the system perfectly, I need to ramp up the gain. Right now, the gain for the position is simply 10. Let me just ramp it up to 100 and then rerun this. Okay, now you can see it's much better, but still there is an error between the reference and the actual velocity, and same for the position. So let's ramp this up further. Okay, so it's much better now. It's almost tracking the the reference perfectly. So how did it do that? Well, first of all, once I once I got these A's, I got the reference motion. So they remember that two references, one for the first part and the one for the second part. Those are shown as A and B. Then I pack them into a control parameter, which I then send to this one link RHS, which is the right hand side, as a input parameter params, which basically has saved all these reference motion, theta ref, theta dot ref, and theta double dot ref, though I don't use it. So that goes in one link RHS. Okay, and then you can see that there is a command call to control, and this control basically does the control partitioning. So there we have the MCG and then the reference motion. And then this is the controller, which is based on control partitioning. Okay. Now there is this thing, which is interp, which I've not, well, I think I talked about it briefly in the animation class, but the reason I use interp, what interp does is it interp1 interpolates the values for an intermediate time. Okay, so what this means is, let's say that I have the value for the reference motion at 0, 0.1, 0.2, 0.3, and so on. But I want the value at 0.05, but I don't have 0.05 available. I only have 0 and 0.1. So what interp will do is it will basically find the value at 0.05 by interpolating between 0 and 0.1 using uh, some method. So one of the simplest method is assume there is a straight line between 0 and 0.1 and use that to interpolate for 0.05. But there are other ways to do it, which actually uh, interp will tell you. So if you do help interp1, it throws up um, how it's used. And then it also tells you how you can do the interpolation. You can use linear, which is what is the default, and this is what is done here. But you could do what is known as nearest neighbor interpolation. You could do spline, you can do cubic, and so on. Okay, and then all you need to do then in that case is just include this method. So for example, you just say the method here. So it'll be spline, and then it'll do spline interpolation. It's very easy to use. Okay, so that's the control that's being called by the right hand side, which basically has the equations, and that's all which is there to the code. Okay, now let's see the other example. This is the double link pendulum. So again, I'll open the similar files to link main, then the right hand side, the control, and then the trajectories. Okay, so these have the same meaning as a single link pendulum, right? So the single link pendulum, there's a traj file which basically generated the trajectory. This one does the same thing. Assume a third order polynomial for the first link, and since there's only one trajectory or one reference motion, I just have to find 4 coefficients. I run this and it will throw out 4 constants, which I then need to copy paste. These ones I need to copy paste into link main. Okay, so I just separated those things out just to make it easy. So that should be somewhere here, right here. Yeah, that's been copy pasted. Similarly, you can the other file, the second link, does the same thing. It basically will throw out 2 of these things. One would be the A's for the first part, swinging backwards. The calf muscle swings backwards, and then the forward motion, which is the second set of parameters, which again have to be copy pasted into link main right here. Okay, so let's run this and see what happens. Okay, so here the tracking looks perfect, and that's, you can actually even see so there's a dashed line, which is the reference motion. You can barely see it. It's beneath the red line over here. But this is for link. This is basically link 1, link 2 position, link 1, link 2 velocity. Okay, and this is just because I started off with a very high gain of 1000. If you reduce the gain, you will see that it starts. If you reduce the gain, you'll see that it starts not tracking the trajectory. You don't quite see it in the animation, but you'll see that if you do the graphs. Okay, there it is. Okay, let me keep it to 100. And then it also produces the RM root mean square error, which is basically saying what is the difference between the reference motion and the dashed line and the blue line. If you take the sum and then you take the square of that and then take the square root of that, so sum of the squares, square root of the sum of squares, then that's what the RMSE is, and that's for the position, that's for the velocity. Okay, so that's the part on tracking for a reference motion. Okay, so what's Cartesian based control partitioning? Well, so far we've seen that we need to track Q reference, Q ref, Q dot ref, and Q double dot ref, where Q are joint positions. Okay, but most times you are not really, you're interested in tracking Qs, but the things you want to do are in the Cartesian space. So for example, if you want to move the box from point A to point B, then you want to specify the Cartesian position of the box, right? X, Y, Z position as it moves. So in other words, what we're interested in is to see how the end effector moves in the Cartesian space. So however, we are interested in how the interested in tracking and effector position, velocity, and acceleration. So for example, if I write X, capital X, as small x, y, and z of the end effector. So if there is a manipulator, that is the end effector of the manipulator. So that's the end effector, and we want to track the motion of the end effector in Cartesian space, because in Cartesian space the manipulator has to lift objects and so on. So what we're interested in is tracking x ref, x dot ref, and x double dot ref. Okay, so how do we modify what we have, trajectory tracking, to track x ref, x dot f, x double dot ref? So what we do is actually not very hard. So it actually follows from what we've done so far. So what we'll do is, so first we will have x ref, x dot ref, x double dot ref is being defined. Right? Because how we get that? We get it from trajectory generation, which we've talked about before. Then we will find q ref, q dot ref, and q double dot ref from 1. Okay, so how do we get q's from x's? We've seen that x is f times q, right? This is the forward kinematics. So given the position of the joint, we can find where the end effector is going to be. So given q, we can find where x is. So then if you want to find x ref, we simply have to put q ref. So then if you want to find q ref from x ref, then all you need to do is invert the f, which is the forward kinematics. So we get x ref. This is the inverse kinematics we've also done in the past. In fact, from the homeworks you did with the manipulator, you actually only did inverse kinematics like so. You inverted f using fsolve, and that basically enabled you to draw different shapes on with manipulators. Now we also need q dot and q double dot. And so what we do is we basically write this, we basically differentiate this expression. So we have x dot ref equals, now when we differentiate f, if you remember, the derivative of f is actually the Jacobian, right? Times, so it will be df dt, right? That's because that's what we're doing. We're taking the derivative with respect to time. But then that is df dq dt, which is the Jacobian times q. Sorry, let me write this as x dot. This is more generically written like this. So x dot equals df dt, which is j times q dot, right? So we can now write x dot ref equals j times q dot ref. And so if you want to find q dot ref from x dot ref, which is given to you, then you simply invert j. So I'll write that on the next page. So now we have q dot ref is equal to j inverse x dot ref. Okay. And then the final thing is we need to get q double dot ref. So then we take x equals jq, differentiate x dot equals jq dot, x double dot equals jq double dot plus j dot q dot. This is just using the chain rule. And then we can get q double dot, which is what we're interested in, from x double dot as x double dot minus j dot q dot. And so q double dot ref equals x double dot ref minus j dot q dot. So we've now found what q ref is, q dot ref and q double dot ref. And the third step is simply use control partitioning in joint space. So that is what we wrote down the last class, in which I showed you just some time back. It's basically m hat q double dot ref plus kp q minus q dot ref plus kd q dot minus q dot ref plus c hat q dot plus times q dot plus g hat q. Okay, so once we do that, we'll see that the manipulator actually follows the trajectory you want, because now we have found a relation between q ref and x ref. So the last thing I'll do is I'll show this, I'll demonstrate this with a manipulator drawing the figure 8 or a lemniscate. So a two-link manipulator, and the task is to draw the lemniscate, the figure 8. Okay, so the lemniscate is, some of you might have done the lemniscate for your homework. The equation of a lemniscate is x equals x0 plus a sine theta, sorry, 2 theta, and y equals y0 plus b cosine theta. Okay, where a 2a is this, 2b is this, and then the center point is x0, y0. Okay, now, as I said, you need to define a reference motion. So what you can see is that if you differentiate x dot, do that twice to get y double dot, you will see that when theta dot goes to 0, x dot and y dot equals 0. Okay, and same for the second derivative. So all you need to do is you need to just specify conditions on theta to ensure that the trajectory is smooth. So what we do is we specify theta at time t equals 0 equals 0, starts at 0. At some time capital T, it should be 2 pi, because we need to complete the lemniscate, the figure 8. And then we just specify that the velocity is 0 at the start and end by specifying a condition on theta instead of x and y, because these are 0 once theta dot and theta double dot is 0. So from this, we write a fifth order or polynomial for theta. Okay, and then solve for a's based on the 6 conditions. That's not new. We've done that with for trajectory generation. So I'm going to show you how to draw the lemniscate using MATLAB. So you can see that it starts off slowly because the number of dots are more, and then it ends slowly. That's ensuring that the position, the velocity and acceleration, the start and end are as slow. Now you can see that it's not quite tracking what you wanted it to do, and that's because the gains are too low. In fact, I started this gains with a gain of, I think, about 10. So let me ramp it up to 100 and see if it does better. Okay, it's much better. You can see that tracking is significantly better than previous. And if you keep ramping this up to say 1,000, then actually you'll see that there's actually no visible difference between the reference and the actual velocity and actual position. And you can also see that the RMSE value goes down to almost close to 0, 1e negative 2. Okay, there's the tracking for the velocity and tracking for the position. Okay, so how did I do this? Well, so a few files here. The file which generates the trajectory is right here, which is again based on the same idea, which is you find the fifth order polynomial, find the constants by differentiating the values. And then there is the j and j dot, which are part of finding the x ref and x dot ref and x double dot ref. And what I did was I actually included the equations of motion, which can, if you run this, it'll actually give you all the things you need in order to put in the right place. And it actually tells you where to put them. So copy paste in Jacobian end effector, copy paste in Jacobian dot end effector, and so on. Okay. Let me just do one more thing and I'm done. Tooling, traj. So this is the place where actually everything comes together. I get the reference motion, x dot, x double dot, y dot, y double dot, and then I use fsolve to get the value for the q, right? And then I use j inverse times x dot ref to get theta dot, and then I've used j dot and j inverse to get theta double dot. Okay, and then once you do that, then it's all a matter of putting this in controls, which basically takes in those values, use control partitioning, and then just tracks the reference.